Welcome back. This is Signal and System Part 2, Chapter 5.1, Introduction to ZTransform. In this part of the video, we'll talk about the introduction to ZTransform with the following focus of relationships, definitions, why, and some examples, ROC and two-sided transform. The relationship of ZTransform is very similar to the Laplace transform. Here, in the previous lectures, we have converted xt into xs, ht into hs, and the convolution operation in time domain becomes a multiplication. And that was one of the main reasons why we are interested to perform transformation, because transformation allows us to perform convolution, which is a very expensive business, into multiplication. Similarly, in the previous lectures, we saw that there was no difference. One is doing in time domain and the other one doing in the frequency domain, because we can perform transformation to the frequency domain and from the frequency domain back to the time domain without any loss. So what about the Z-transform? Similarly, if we have the system x of n, which is the input, going into a discrete time system h of n, then the output is still a convolution between h of n and x of n. Here, remember, we are now in discrete time, where n belongs to integer values. When we perform Z-transform, we get x of z. When we perform h of n, we get h of z. Convolution in time becomes multiplication in frequency as well. And this is one key relationship between the Z-transform and the Laplace transform. They are actually almost the same. One is dealing with continuous time and one is dealing with discrete time. Let's now define the bilateral Z-transform. The bilateral Z-transform takes the input signal x of n, which is discrete time. So n belongs to integer and nothing in between. Okay, so it's not like x of t, where t is the real number. Now, to perform Z-transform, we use this equation, and then we'll get x of z. So it takes a sequence of numbers and just append it with z minus n. So what is z? So z is a complex number. And so it takes a sequence of numbers and convert it into, actually, what do you think this is? This is a series. Adding terms after terms is a series. So look at x of z. And when we study the equation properly, each of these terms becomes this, becomes this, becomes this, and so on through the infinite summation. What have we just done? We have taken a sequence and start to add them up. And this is a series. And not only that, we are multiplying with z. We're creating a polynomial out of it. So a Z-transform is nothing but taking a sequence of numbers, converting into a series or a polynomial. And of course, it is an infinite if the sequence is infinite. Now, please become alert to z. So z is a variable. And this variable is up to us. Well, in fact, well, not really up to us, it's the entire complex plane. That means we're going to put z for all of z as a complex numbers. Z equals to 0, z equals to 0 plus I, 0 plus 2i, 0 plus 2.1i, and so on. And then, of course, 1 plus I, and so on and so forth. The whole entire plane of z. So this is the real number. This is 0, this is 1, this is 2, this is minus 1, minus 2. This is j, 2j, minus j, minus 2j. And therefore, this whole thing is the entire z plane, or the complex plane. So to recap, x of n is the input. Performing Z-transform gives us x of z. Let's have a quick revision of the complex variable z. if this line, the horizontal line, is the real part of z in this position where it crosses, this is the number 0. The vertical line is the imaginary line. And we can express z in two ways. The typical way is what you do is you drop this, and this is the real number a, and you project this. This is jb. So z is a plus jb. This is the rectangular representation. We sometimes use another representation called the polar representation, or the complex exponential representation. In this example, here is the complex exponential. We use r as a radius, as a distance from the origin to the point. That is not enough. We need the angle, because we need, since we are given only r, then r will form a circle around the origin. So where exactly is a circle? At this point, we need the angle. So it will be r e j omega. Omega is the angle anti-clockwise from the origin. Oh, sorry, anti-clockwise from the real line, positive real line. Now, remember the Euler's formula? Ej omega is equals to cos omega plus j sine omega. So what is Rej omega? It's nothing but r cos omega plus j sine omega equals to r cos omega plus r or jr sine omega. And then this is equals to a plus jb. Therefore, a is r cos omega and b is r sine omega. So this relates the rectangular to the polar representation. Now we're going to manipulate this equation a little bit. X of z is, for different z, is Rej omega. Well, if we substitute it into the expression of ZTransform, which is the input, multiplied by different z. So this is z, and remember, it is not z but z minus n. Okay, now if we represent z as Rej omega, we can open up the brackets to distribute. So this is x of n times r to the power minus n multiplied by e to the power minus j omega n. This looks very familiar. This is a signal. For example, let's call this y of n, e minus j omega n. Later on, you'll realize that this is the discrete time Fourier transform of y over n. Okay? But now we can interpret it as we have taken the signal x of n and we have multiplied it with r minus n. And if r is greater than 1, you realize that if r is greater than 1, then r to the power minus n becomes smaller and smaller. So this helps us to deal with different type of x of n and make x of n the sequence finite, so that the summation becomes finite, and therefore the Z transform then exists. In fact, if you look back at the Laplace transform, it's exactly the same idea. For Laplace transform to apply to many different signals, what happened is that we multiply it by e minus sigma t and make x of t decays as t goes to infinity. So here we have x of n minus times r to the power minus n. And lastly, we now talk about the unilateral Z transform. In the bilateral Z transform, the index grows from minus infinity to infinity. However, typically, we are interested only in causal signal. So we have a subclass of signal that only exists from positive time. Therefore, we are not interested in n equals to negative infinity to infinity. Now, if that is so, then this is called the unilateral Z transform. That means we ignore the negative time. Okay. Now, one of the reasons why we do this is because bilateral Z-transform does not have unit inverse. And if our problem is normally causal signals, then we need only to apply the unilateral Z-transform. And the analysis is simplified because we have only one type of ROC, which is the external to the pole. So we'll see ROC later in the slides. Thank you.